Welcome to the deep dive. Today, we're jumping into large language models, LLMs. And look, it's impossible to ignore how powerful they are. They've changed so much, content creation, customer service, all sorts of things. But there's this growing problem hiding behind all that capability. They are just getting incredibly big. And that size, it's not just a technicality, it's a real barrier, a huge challenge for anyone who actually wants to use them or deploy them effectively. So that's our mission for this deep dive. We're going to unpack a really interesting new transformer architecture. It's called Mixture-of-Recursions, or MoR. We'll look at how it tackles this core scaling problem head on, get into the weeds of how it works, and explore what it could mean for you, whether you're building AI or just using it. Okay, so let's first really dig into this central issue. Why are these LLMs, as powerful as they are, kind of hitting a wall? Well, their ability to do amazing things, like writing really convincingly or generating complex code, it's tied directly to how big they are. More parameters, think of them like billions of tiny adjustment knobs. The AI tunes while learning usually means smarter, more capable models. But yeah, scaling them up like this comes with a massive cost. The memory they need, the sheer amount of computation. It often becomes, and this is a quote from the researchers, untenable. And that's not just, an academic problem. It really puts the brakes on innovation. Trying to run these massive models is like needing a supercomputer in your office. It basically locks out smaller organizations, drives up costs massively, and just slows down how widely this powerful AI can spread beyond, the big tech companies with those huge data centers. It's a serious bottleneck.
It absolutely is. And it's worth remembering the AI community has been chipping away at this efficiency problem for a while now. There are really two main avenues people have explored. First, there's what we call parameter sharing. It's basically about getting more bang for your buck, parameter-wise. Things like layer time, for instance. That's where you reuse the same learned weights, and those knobs you mentioned, across multiple layers in the network. So instead of learning unique weights for every single layer, you share them. This cuts down the total number of unique parameters you need to store and train, reducing complexity. Then the second main approach is adaptive computation. This is more about being smart with the processing power you have. Instead of just throwing the same heavy computation at every single piece of data, these methods let the model adjust how much work it does based on the input. A good example here is early exiting. Basically, it allows simpler inputs or tokens like the individual words or parts of words to finish processing earlier in the model. If the model figures out, okay, I understand this part sufficiently, it stops processing it.
That avoids wasting compute on the easy bits.
Okay, so you got parameter sharing making models leaner, and adaptive computation making them smarter about using resources. Both tackle efficiency, but from different angles. But here's where it gets really interesting. The big challenge that kind of holy grail researchers have been after is figuring out how to effectively combine both approaches into one elegant architecture. Getting that synergy, that unification has been really tricky. Until now, maybe? And that's exactly the opening for Mixture-of-Recursions. MoR, it's presented as this novel solution, a new transformer architecture coming out of research at KAIST AI and Mila, designed specifically to bridge that gap.
Exactly.
Its core idea, its innovation, is that it's a framework built to combine parameter sharing with adaptive computation, all aiming to tackle those massive computational costs of LLMs. It's trying to get the benefits of both worlds in one package.
Right, and it's not like they conjured this out of nothing. Moore builds upon an earlier idea called recursive transformers. So your standard transformer model is like a tall stack of different layers, right? Each layer is unique in its own parameters. Recursive transformers do it differently. They take a smaller set of layers, sharing parameters, and apply that set repeatedly. Think of it like partitioning the model into a few recursion blocks. Each block is the shared pool of parameters. This setup lets you perform more computational steps, sort of like deeper thinking, without actually making the model physically bigger in terms of unique parameters. It's like having a really versatile multi-tool you use again and again instead of needing a separate specialized tool for every task.
Ah, okay, that makes sense. Using the same tools more effectively. So MoR takes this recursive idea and adds some twists. Let's unpack this. How does MoR actually make it work? Sounds like there are two key ingredients.
Yes, exactly. Two key components that enhance the recursive approach. The first is what they call a lightweight router. Its job is pretty clever. It looks at each individual token coming into the model and intelligently decides how many times the shared layers, the recursion block, should be applied to that specific token. It assigns a recursion depth. So essentially, it's deciding how deeply the model needs to think about each piece of information.
Interesting.
It's sort of analogous to the routing you see in mixture of experts, or MoE models, where a router sends tokens to different specialized networks. But here, the experts aren't separate networks. The experts are the different levels of recursion depth itself. So the router directs traffic based on how much processing is needed. This token looks simple, just one pass. Or, whoa, this one's complex, let's apply the layers multiple times. This dynamic allocation is key. It focuses the computation power precisely where it's most needed, avoiding wasted effort on simpler parts of the input.
So the model itself is figuring out token by token how much effort to expend.
Yeah.
That's a really smart way to allocate resources. Okay, what's the second piece of the puzzle?
The second key component is a more efficient key value KV caching strategy.
Right, KV caching. That's pretty standard for speeding up generation, isn't it?
It is. It's a standard technique. Basically, when an LLM generates text, it often needs to look back at information it processed earlier in the sequence. KV caching stores these intermediate computations, the keys and values from the attention mechanism, so the model doesn't have to recompute them constantly. It's like a short-term memory, and it speeds things up a lot, especially during inference.
But you said it can be a bottleneck.
Yeah, particularly in recursive models. Because you're applying the same layers repeatedly, that cache, that memory, can grow very large and become a bottleneck itself, eating up a lot of memory bandwidth. MoR tackles this with what they call a recursion-wise KV caching mechanism. What it does is it selectively stores and retrieves these key value pairs only for the tokens that are still actively being processed at any given recursion step.
So it's more targeted.
Exactly. If a token has finished its processing early because the router decided it didn't need more recursion, its KV pairs aren't kept active unnecessarily. This targeted approach drastically cuts down on memory traffic. It improves throughput, basically, how much data you can push through the model over time. And a really nice benefit is that it works without needing complicated changes after the model is trained, which is often a headache with other optimization methods.
Okay, so you put those two together. The smart router deciding the thinking depth for each token, and this efficient selective KV caching, it paints a pretty clear picture. And the researchers summed it up nicely in the paper, didn't they? They said something like, in essence, MoR enables models to efficiently adjust their thinking depth on a per-token basis, unifying parameter efficiency with adaptive computation. That really captures it. Okay, that's the theory, and it sounds compelling. But what about the practice? How do they actually test MoR? What did the results show?
Right, the proof is in the pudding. They trained several MoR models, ranging in size from about 135 million parameters up to 1.7 billion. Then they benchmarked them carefully against standard, or vanilla, transformer models, and also against regular recursive models without the MoR enhancements. They looked at things like validation loss, which measures how well the model predicts unseen data, and also performance on various few-shot learning tasks.
Yeah.
That tests how well the model adapts to new tasks, with just a few examples.
What were the gains?
The results were quite significant. First off, accuracy versus parameters. When they gave models the same total amount of compute for training, the MoR model actually achieved a higher average few-shot accuracy, 43.1% versus 42.3% for the vanilla baseline. And here's the really impressive part. It did this while using almost 50% fewer parameters.
Wow, okay. Better accuracy with half the parameters. That's substantial.
It really is. Fewer parameters means less memory, potentially less compute needed at inference time. Big win. Second, training efficiency. When they trained models on the same data set, the MoR model finished training 19% faster, and it used 25% less peak memory during that training process compared to the vanilla model. Again, that translates to faster development and lower infrastructure costs.
Faster training, less memory. Ashek, what about scalability? Did it hold up as models got bigger?
Yeah, that's important. They found that while MoR slightly underperformed the vanilla model at the very smallest scale they tested, 135 million parameters, that gap disappeared quickly as the models got bigger. For models over 360 million parameters, MoR either matched or actually beat the standard transformers, especially when the compute budget was limited. And finally, inference speed actually using the model. MoR's design gives a big boost to throughput. One specific MoR configuration they tested achieved a 2.06x speedup compared to the vanilla baseline.
2 times faster inference. Okay, those are some eye-opening numbers. Reduced parameters, faster training, less memory, faster inference.
So let's translate this. What does this all mean in practical terms? For a company actually trying to use AI, maybe at scale, what's the real impact of, say, a 2x speedup or using 50% fewer parameters? That's the crucial question, isn't it? Sangmin Bae, one of the paper's co-authors, provided some insight on this. He explained that reducing the model size and that KV cache footprint directly allows you to run inference on many more samples at the same time using the same hardware. This means you can process more tokens per second. And critically, it makes handling much longer context windows, feeding the model more information at once, much more feasible.
Right.
So think about what that means for a business. It's not just shaving off milliseconds. It could mean handling twice the customer support queries with the same servers, or being able to analyze much longer documents or conversations. Or maybe they can maintain their current throughput, but drastically cut their energy costs and hardware needs. It fundamentally changes the economics and accessibility of deploying powerful AI. It could lead to really significant operational savings and open up entirely new applications that were previously too expensive.
That really could be a game changer, especially for companies that aren't hyperscalers. But you mentioned the results came from models they trained from scratch. That's a big investment. How might a company adopt more without having to go through that massive retraining process? Is there a way to maybe adapt existing models?
That's a very practical concern, and yes, Sengman Bay addressed that too. He suggested that uptraining existing, perhaps open source models is likely a definitely more cost-effective approach. So instead of starting from zero, you take a pre-trained model and fine-tune it, adapting it to use the MoR architecture. He felt this uptraining approach could be more suitable and efficient, at least until MoR's scalability is even more widely validated. It provides a lower barrier to entry.
And that makes sense, a more gradual adoption path. And it sounds like using more gives developers some new dials to turn, new knobs to fine-tune that trade-off between performance and efficiency for their specific use case.
That's exactly right. Adopting MoR means you have choices to make about, for instance, the number of recursion steps versus the depth. The paper suggests that the optimal settings will highly depend on the specific deployment setting. You might configure it differently for a simple task versus a very complex one. It empowers teams to experiment and find the sweet spot based on their needs, using the paper's findings as a guide, rather than being stuck with a single rigid structure.
We focused heavily on text, on LLMs. But you mentioned earlier that MoR's principles might be broader. Does this have potential beyond just language models? Could it apply to other kinds of data?
That's a really exciting angle. The authors point out that the MoR framework is fundamentally modality-agnostic. Its core idea is the shared parameters through recursion and the adaptive computation via the router deciding processing depth aren't inherently tied to text.
Oh, okay.
So yes, this opens up possibilities for major efficiency gains when processing other complex data types like video or audio. Imagine applying this to video processing. The model could dynamically decide to use more recursion, more thinking depth on frames with lots of action or complex changes, but less on relatively static scenes.
Right, focusing the effort where it's needed most.
Precisely. Same for audio, maybe processing complex speech or music more deeply than silence or simple background noise. This could lead to even greater cost savings and performance boosts in those domains, making large-scale AI analysis of multimedia content much more practical. As the paper concludes, MoR really does offer an effective path towards achieving large model capabilities with significantly reduced computational and memory overhead. It seems like a promising direction for AI efficiency across the board.
Okay, so let's wrap up this deep dive. Mixture-of-Recursions, MoR, emerges as a really potent new architecture. It tackles that critical LLM scaling problem by cleverly bringing together parameter efficiency and adaptive computation. And the results seem to back it up: significant improvements in speed, memory usage, training time, and even accuracy in some cases. It feels like a genuine step towards making cutting-edge AI more practical and accessible.
Absolutely. And maybe a final thought to leave you with. Consider what it means for a model to dynamically adjust its depth of thinking for each piece of information it sees. Beyond just efficiency, could this lead to AI systems that are, in a sense, more aware of the complexity within the data, less brute force, more nuanced? What kinds of new capabilities might emerge from AI that can truly adapt its processing effort on the fly? Something to think about.
A fascinating question indeed. What stood out most to you during this exploration of MoR? We hope this gave you some valuable insights. Thanks for joining us on the deep dive.